Welcome back again. We are in the midst of discussing Unit 7, which had to do with equilibrium and elasticity. We have several objectives in this lecture. However, we want to do a little bit more with static equilibrium. Then we're going to move on to the second part of Unit 7, which is elasticity. It's actually a pretty small part of the unit, so we're going to completely cover that in this lecture. And finally, at the end, I'm going to introduce to you Unit 8, which has to do with gravitation. So, to recap from last time, we discussed equilibrium and defined it as being a state in which an object has no net forces and no net torques on it. And we did a couple examples. We talked about how you can define your reference point to make the calculations simpler. So I want to do one more example of this kind of static equilibrium problem before we move on to discuss elasticity. So this problem is near and dear to my heart. It has to do with a climber, and this person is at an angle with respect to the rock face of 30 degrees. We want to start by drawing an extended free body diagram of the climber. And what we want to know is the static frictional coefficient between the rock face and the climber's feet. Because of course, if he slips here, yes, he's tied in, but then that's going to cause his whole legs to come free here. Okay, so we want to include all the forces that are required here. So think about how many forces that ought to be. You've got a normal force pushing from the rock face onto the climber. You've got a tension force. You've got a weight force, okay? And you've got the frictional force as well. So that adds up to 4 forces. So on the extended free body diagram, if I include all of those forces, it ought to look something like this. Notice that the angle phi is measured here as 30 degrees with respect to the rock face and the rope. Okay, that is not the same as this angle here, which is theta of 40 degrees. Okay, so the next step we're going to take is to apply the idea of adding up the forces in each direction. So when I'm looking at this, I see that most of the forces naturally align to either the x or the y direction, except for the tension force. I'm going to have to break that up into components here. So in the x direction, I've got the normal force of the rock pushing outward on the climber's feet, and I've got the component of the tension that is pointing in the negative x direction here, which is t sine of phi. Okay, hopefully you can see why that's the case, as it is located opposite of the angle phi. In the y direction, I've got the y component of the tension force here, so that's going to be cosine of phi times t. And then I've got the static friction pushing up on the climber's feet, and I've got the weight force pointing down. The sum of each of these forces in each direction needs to be equal to 0 if this climber is to be in static equilibrium. So the first equation basically just tells me that the normal force is going to be equal to this y component of the tension. The second equation can be simplified a little bit, well, maybe not simplified, but fleshed out a little bit by specifying what we mean by the friction force, that this is mu times the normal force. And what we learned from the previous equation was that the normal force equaled t sine of phi, so I can make that substitution in here to arrive at this expression here. In addition to knowing about what the forces are doing, we want to add up the torques to ensure that we're in static equilibrium. And so we want to choose a reference point for our rotational axis that is sensible and minimizes the number of forces that we have to include, the number of torques we have to include. I've gone ahead and chosen this O as my reference point, because at that point the friction force and the normal force are have zero lever arms, so they are not going to be included in my sum. Instead, when I add up the torques, I will have the weight force crossed with the lever arm and the tension force crossed with the lever arm. Okay, the sum of those torques has to equal 0 if the climber is in equilibrium. And so when I carefully perform the magnitude of these cross products here, I'm going to get that the force of gravity times the length here from where he's attached to the end times sine of theta is going to give me my cross product, because this is the angle between the weight force and the lever arm. As you see, these are alternate interior angles, so this is also theta. We're going to do the same thing with the tension. So we've got tension times the lever arm L times sine of the angle between them. Okay, and we have to figure out what that angle actually is. Okay, so if you are careful to analyze the situation here, you can see that it's going to be 180 degrees minus theta minus phi. That's one way of expressing it. Okay, and so when I solve then for the tension, I arrive at this equation right here. Okay, so I have an expression that I got from the use of the sum of the forces and being in equilibrium with the forces, and then I have an expression that I found by adding up the torques. And so what I want then is to simplify the first equation and combine these two things together, and what I will finally arrive at is the expression that you see in the box. Okay, so when I get to this point then, I can see that the coefficient of static friction can be computed due to the fact that I know these angles, right? And the only thing then that is left is to figure out, eliminate what this tension is. And so that we got from this equation here, making that substitution in, we now have everything in terms of given information. The mass of the climber, the angles, and those get inputted into this expression to give us what the frictional coefficient is, which is 1.19. Okay, so finally, that basically wraps up the stuff I wanted to say about equilibrium. The last part of Unit 7 has to do with elasticity. And so we're going to look in particular at elastic deformation. So I want to cast your memory back to whenever we were talking about Hooke's law, and we had this equation that F was proportional to Kx. And so if we think about that in terms of solving Hooke's law for K, there's a ratio of force over delta x that gives us some constant. In general, we can think about what we call elastic moduli, which are constants, as a general stress over a general strain. Okay, and so Hooke's law can be generalized in this sense. Let's say perhaps that we're looking at changing the the length of something, either stretching it or compressing it, making it longer in this direction or shorter in that direction. For this kind of linear deformation of a solid, what we're doing is we're applying a stress over a strain, where we apply some sort of tension force per area over some length change compared to the original length. Okay, so this, just like in Hooke's law, is a constant, except that my units are a little different here. This is going to be units of pascals. in the numerator. Okay, because this is a force over an area, which we also know as pressure. And the SI unit of pressure, Newton per meter squared, is a Pascal. And then in the denominator we have a meter over a meter. So actually this modulus is also going to have units of pascals. So different substances are going to be more easily or with more difficulty stretched or compressed. So if we look at a chart of different materials, we'll see that things that are rather stretchy are going to have a very low Young's modulus for their constant. And things that are not very stretchy, such as steel, are going to have a very high Young's modulus. So you can think about this a little bit like a measure of stiffness. So a conceptual question for you, if the Young's modulus of steel is greater than a particular unknown, than what we would have for a particular unknown material, what does that mean about how the materials will compress under construction? Okay, so if the Young's modulus is greater, that means that it is a measure of the stiffness. So the stiffer that the material is, the less able it is to be compressed. Okay, in 3 dimensions, it's sometimes helpful to think about a different kind of stress over strain that has to do with a different constant that we call a bulk modulus. This is often something that we look at when it comes to fluids. And so we're still looking at stress over strain here being constant. And sometimes on charts you're looking at the inverse of this constant, and we call this, instead of bulk modulus, we're looking at compressibility. And so this also ties into the idea of pressure, because pressure is again force per unit area. So when you're looking at this bulk modulus, you have a delta pressure in the numerator, and remember that that is defined to be force over area. So for different fluids, something that is very compressible will have a small bulk modulus, such as gases. Something that is more incompressible will have a large bulk modulus, such as water compared to gas, or lead even more. And the last kind of elastic deformation that I want to discuss is the shear modulus. So shear modulus is another constant that we might have, which again depends upon the substance, where we're looking at stress over strain, but this time we're applying the stress at angles so that you are creating a shearing action. This is a force in this direction and a force in this direction. And so this stress over strain will give me my shear modulus. Some things are going to respond more or less to that stress over strain. Of course, just as I said before with Hooke's law, it is not always a perfect law in the sense that everything is linear. At some point, if you stretch something or compress something too much, the deformation you're producing may become permanent. So this is only an approximation in a certain region where stress over strain obeys this linear relationship. Okay, so that basically wraps up Unit 7. I want to move on then and introduce you to Unit 8. We will not get terribly far with this today, but we will continue this in the next lecture. There are a number of topics that we're going to discuss with gravitation. The very first topic I want to discuss is Newton's universal law of gravitation. So this law tells us that everything massive in the universe is going to attract to any other thing massive in the universe, and that force is going to be proportional to the product of the masses and inversely proportional to the square of the distances between them. So that's a lot of words, it's a lot easier and more compact to write that as an equation. F equals g m1 m2 over r squared. Now don't get confused, this g is not the same as the little g that we used in Newton's laws when we were talking about 9.8 meters per second squared. This is a different g. This g applies anywhere in the universe. It is therefore called the constant of universal gravitation, and its value is given right here. As you can see, this is a very small number, much smaller than the 9.8 that we're looking at before, and of course the units are entirely different as well. This constant can be verified experimentally, and this was done so in 1798 in the Cavendish experiment. In actuality, the way it was thought about then was a way of measuring the Earth or weighing the Earth, but that in principle it will give you the constant, the value of capital G. And as I said, it's good anywhere in the universe. Oh, and one other note on this slide that I should have said is that this law of universal gravitation is an example of what we would call an inverse square law of nature. You're going to run into a lot of these in your studies of physics, where as the distance between two objects increases, the force between them decreases like that distance squared. Gravity is one example. Next, when you're taking Physics 2, you'll learn that the force of electricity also obeys an inverse square law relationship. The brightness of light does this as well, so it's a very common sort of thing that recurs in nature. So one nice thing that fits nicely with the universal law of gravitation is that you can see quite plainly that it agrees with Newton's third law. If every mass attracts every other mass, with this relationship that we've just written out, then when we say, for example, write out what the force on the moon is due to the Earth, we get g m of the Earth times m of the moon over r squared, the distance between them. And when we figure out what the magnitude of the force of gravity on the Earth due to the moon, we get the same thing. Okay, we might write moon first, but it doesn't matter. It's the product of the two in the numerator, which is essentially the same. And that's in agreement with Newton's third law that tells us that when we have action-reaction pairs, the forces should be equal and opposite. It's worth noting that the force of gravity for large objects like this, like a sphere, is acting as if the mass were concentrated at the center of the sphere. Okay, so this little bit here has to come all the way out here, right? We're acting like it's all at the center of the Earth. Okay, so based on that information, let's see if we can take a scenario and understand a few of these scenarios conceptually. So let's say that we have two satellites orbiting the Earth, and satellite B is 3 times more massive than satellite A, but it's orbiting at a distance which is 3 times greater than satellite A. And you want to know which one is experiencing a greater force of gravity due to the Earth. Well, in the case of satellite B, I've got G times 3 times the mass of A, right? Times the mass of the Earth over 3 times the distance between the Earth and satellite A, all squared in the denominator. This is going to give me 9 in the denominator and 3 in the numerator. So when I compare that to the force for satellite A, I can see that it's only 1/3 of the value of the force on A. Okay, so that is to say that A is still experiencing a greater force, even though it's less massive, because it's that much closer, and that inverse square relationship means that the force drops off more rapidly than you might suspect as a function of the distance. Okay, so let's take another example. Which of the following is going to give us the largest gravitational force? The gravitational force that the sun exerts on the Earth, the gravitational force that the Earth exerts on the sun, or are they the same? Well, as I alluded to before, Newton's third law still is a thing, and if we have a force of gravity on one object, it stands to reason that we have an equal and opposite force of gravity on the other object. So their magnitudes are the same. It's just that, as we said before, anytime we had this situation where it seems counterintuitive, how could the force on my little smart car be the same as the force involved in a collision with a big Land Rover? Well, it has to do also with how massive you are and how you respond to that amount of force. Because the sun is so much more massive than the Earth, it's the Earth that's going to be orbiting the sun, even though they're experiencing the same amount of force. That amount of force to the sun is relatively small potatoes. All right, so one more conceptual example, and then we'll do one where we plug in numbers. So in this example here, what we're trying to do is find a spot where a spacecraft could be placed where the net force on it would be approximately 0. So we want its pull to the Earth to be balanced with the pull to the Moon. Now we know this can't be at the direct center because the Earth is more massive than the Moon. So if I put it at the center, it's going to be more attracted to the Earth than it will be to the Moon, and that won't yield a net force of 0. That means that I've got to be a little closer to the Moon, or another way to think about it, further away from the Earth, in order for these forces to be approximately the same, and so this corresponds to choice C. Okay, so let's take basically that same scenario, only now we're just dealing with generic particles, and we want to place a third particle in between particle 1 and 2 in such a way that it experiences a net gravitational force equal to 0. So what I want then is for the force of attraction here to equal the force of attraction here. I can call this one F13 and this one F23. And what I want is for them to equal one another. Based on the distances that are indicated here, that means force 1,3 is essentially G m3 m1 divided by the distance between them squared. Well, the distance between them is this whole distance minus d. Okay, and then F23 is G m2 m3 over this d squared. As you see, the g's are going to cancel, and I can make some simplifications. Also, the m3's will cancel. I can make some simplifications here. And what I'm attempting to do is isolate this d so that I can figure out exactly where to place particle 3. Okay, when I do the algebra and crunch through the numbers, what I find is that d should equal 0.367 meters. In other words, it's going to be closer to particle 2 than to particle 3, which is sensible if you think about it in terms of particle 2 being less massive. Okay, a couple more conceptual examples and then we will call it a day for now. Let's take this example here where you have a spacecraft in the midst of 4 different planets, or you could think about them as stars. So if you are where this blue spacecraft is located, what is going to be the net force on the spacecraft? Well, these two objects here are more massive, but they are farther away. And remember that the distance gets squared in the denominator, so this serves to weaken the force more so than this increase of mass would. And so we will find attraction more to these two masses, and if I think about what the net result will be, the y components effectively cancel, and what I have is a net force in the direction of A. Okay, so let's take it back to the Earth, for example, for a second, and revisit this little g. I was careful to make you understand that the capital G that I just mentioned is not the same as this little g that we have used before. Now, when I told you the value of little g, I just basically asked you to take my word for it that it was equal to 9.8 meters per second squared. But now that we have the tool of the universal law of gravity, that F equals capital G mm over r squared, we can actually couple that with Newton's second law and say, well, if this is the only force at work on some mass little m, then this universal gravitational force should equal m times a, where a is my acceleration due to gravity. And now all I need to know is the mass and radius of the Earth to figure out then and compute what little g is. And lo and behold, if I solve this equation here for the acceleration due to gravity, notice that the little m's cancel, then I find the value 9.8 meters per second squared. And this also makes it clear that it doesn't matter whether it's me accelerating or a giant elephant or a small pebble. The mass of the object being accelerated doesn't matter near the surface of the Earth. That cancels out of our considerations. And the acceleration rate due to gravity is the same for all massive objects on the surface of the Earth. And it's equal to this value here. Now, of course, I'm simplifying a little bit because in actuality, the shape of the Earth isn't a perfect sphere, and there are topography considerations as well. And when you are at a height above the surface of the Earth, then it might be enough to actually become something that you need to consider. So if you are at a significant height above the Earth, then we're going to include this height, if it's non-negligible, in our expression for the gravitational constant. So instead of just being at approximately the radius of the Earth, you're at the radius of the Earth plus some height h. Maybe it's even a low Earth orbit satellite. Then when I perform this same calculation and figure out what the acceleration rate is due to gravity, I see that it actually does depend on the height, which is sensible, and the larger this height becomes, then the acceleration rate will drop off. So the upshot is that capital G is going to be a universal constant everywhere in the universe. Little g is not, but it can be computed using Newton's laws and what we know about the mass of the Earth and the radius of the Earth. And of course, you can imagine doing this on any planet and plugging in that planet's mass and that planet's radius to figure out what the gravitational acceleration rate would be on other worlds as well. And we will actually take a look at that next time.